Hello, PreCalc. I hope the test went well for you today and that you feel good and strong about it. We are going to go on tomorrow to bigger and brighter things, and it's about time that I taught you how to count. So we're going to do counting techniques, and we're actually in a branch of mathematics called probability. Alright, so this is Wednesday's edition. So you'll be watching this on Wednesday, that's the 5th. Alright, so let's see what we have in store for counting tonight. Alright, it looks like this. What are we counting? We are actually counting, my dishwasher's on, so I hope it's not, the roar isn't too bad. I'm going to leave it on. So, counting. What are we counting? We are counting arrangements. Of course we're counting arrangements. So, let me show you what I mean by an arrangement. Oops. Give myself a little space here. So, suppose we have 3 books. The first book's title is A, the second book B, third book C. So I am counting. How many ways can I arrange these 3 books? Well, if you would write them out with me or ahead of me, I can write A, B, C. I can arrange A, C, B. I can arrange B, A, C. B, C, A. Alright, I'm going kind of slow so you can get it done ahead of me. And how many more arrangements can we find that are all different from one another? Alright, I am out of arrangements. What about you? Notice there are 6 arrangements. 6 different arrangements when you have 3 objects. But we are not going to call them arrangements. No, no, no. We are going to call them permutations. So you can impress your friends and relatives now. So there are 6 permutations of 3 objects. Notice these 3 objects are arranged without repetition allowed. So when you're without repetition, it makes no sense if you have 3 books to have book A, and A, because book A can only be at one spot at one time. So therefore, even though I didn't say without repetition, the actual problem implied it. So we have 6 permutations for 3 objects. How would that change? Now what I want to do is teach you how to count those without writing out all of the different arrangements. Because even if I added a 4th book, book D, it would take quite a bit longer to write them all out and be a little confusing. So let me teach you how to count arrangements. So since there are 3 positions for my 3 books, I'm going to give myself 3 boxes. And I'm going to count in this box the number of ways I can find. How many different ways can I fill the first position with a book? So I could have put A there, I could have put B there, and I could have put C there. So there are 3 different ways that I could have filled position number 1 on my shelf. Position number 2, however, I no longer have 3 ways because I have chosen one of the books for the first position. So now there's only 2 ways that I can fill the second. And lastly, when I get to the 3rd position, there's only 1 way. So I'm actually counting the number of possible ways I could fill each position. And when I finish, I multiply those numbers and I get a 6. Alright, so let's up the ante up to 4. So let's say now I have books A, B, C, and D. So how many permutations of 4 objects, no repetition? So I'm going to think it through with my counting technique. And I have 4 positions on my shelf. How many ways can I fill the first one? I have 4 books to choose from. I could put any of them there. Then I've used up that position with one of my books. So now there's 3 ways I could fill this position, 2 and 1. So I end up with 4 times 3 times 2 times 1. The counting technique requires you to multiply, and you get 24 different ways without listing them all. So, how snazzy. So, can we make a general observation? The number of arrangements for n objects. So since they're objects, then we know there's no repetition. The answer is, does this look familiar? The number 6 and the number 24? Turns out that the number of arrangements for n objects is n factorial. Did you recognize whenever I said earlier, whenever 24 pops up and 120, it seems to be a factorial relationship. So this is 3 factorial, this is 4 factorial, so n objects would be n factorial. Alright. Alright, now let's look just for a moment at some situations that don't follow that rule, because this is going to, what if we allow repetition? So a scenario might be, how many letters? Let's say I have 3 letters this time. How many arrangements, I'll call it, how many arrangements are possible for 3 letters? So up here I actually used letters, but they represented books. But if I actually want to use letters, how many different arrangements are possible? So we said there's going to be 3 positions, 3 letters. So there's my 3 boxes. And this time I have all the letters of the alphabet that I could put in the first position. So I could put 26, I have 26 ways that I could fill that first position. When I get to the second one, it's not like I have 25, because letters can be repeated. There's nothing, so it's inherent in the problem to know whether repetition is allowed or not. If I use A once, it doesn't prevent me from using it again. So I still have 26 letters. And the last position, I have 26 letters. So 26 times 26 times 26. I'm not sure what that is. 26 cubed. But that's the number of ways, the number of arrangements I can come up with letters, taking 3 at a time. So let's look at another situation, and this will be, we're going to add some conditions. So conditions are just like they sound. So I'm going to come up with a scenario where I am going to describe a situation that inherently sets conditions on some of my positions. Conditions on my positions. For example, suppose I want to know how many possible phone numbers, how many different permutations of phone numbers. So phone numbers start with an area code, so I have 3 boxes. Then I have 3 more boxes, and then I have 4 boxes. Just like our numbers are 410-721-6829, something like that. So this is the beginning to figure out a problem with phone numbers. what conditions are there? Well, it turns out someone would have to tell us this, but in an area code, the first box cannot be the number 0, and it cannot be the number 1. I didn't know that, but I guess it's true. So I'm going to actually write down the numbers. Here's are my candidates for each position. So when there are conditions, I'm going to go to the box that has the most conditions first. So that one is already pointed to. So I can't just put any number in. How many ways can I fill this box obeying the conditions, not 0 and not 1? Well, I have 1, 2, 3, 4, 5, 6, 7, 8 more numbers that are possible. When I get to this box and the phone number, it can be any number. So I have all 10 numbers that are possible. And then 10 numbers. And then when I've gotten to this one, we have a number of, I think they can be 10, 10, 10. Each one of these has no conditions. Alright, so these are the conditions I set. Some problems will set other conditions for phone numbers. Some say that this cannot be 1 and 0 as well. But these are the conditions that I've set for this problem. So to find out how many numbers that is, you multiply 8 times 10 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 times 10. Very, very, a lot of numbers. Alright, so that's the conditional one. Let's continue our study by looking at 8 horses. And the horses are in a race. And there's a first winner, first place, second place, and third place. I would like you, before I do, to put in the number of ways that we can fill the first place box. So this is the first place winner, the second place, and the third place. So these are the horses that are going to place in the race. So how many ways could we possibly fill in the first, second, and third? So think that through, determine whether replacement or non-replacement is inherent in the problem, and go ahead and come up with the number. Did you realize first place is up for grabs? Any of the 8 horses, I could fill that box with any of those 8 horses' names. But once I have a first place winner, he can never also be the second place winner. So there's only 7 ways I could fill that, and in like manner, only 6 ways I could fill that. If I multiply those out, I get 336. So that kind of thinking is given a name. And it is like this. These are permutations or arrangements. So it's how many permutations of 8 objects taken 3 at a time. So that symbol represents this scenario. That is a subscript. The 8 is in front and the 3 is in back. And it is read the number of permutations of 8 objects taking 3 at a time. There's actually a formula for that, so we don't really have to go the box route, although I prefer to actually do the box route because it kind of has more meaning to me than just a formula. The permutation of n objects taking r at a time is going to follow this formula. N factorial over n minus r factorial. Let's see if it works for our horse example. So we can see that the permutation 8 goes in for n and 3 goes in for r. So in the formula it becomes 8 factorial over 8 minus 3 factorial. So that's 8 factorial over 8 minus 3, or 5 factorial. And we learned the quick way keeping an eye on the prize. Start writing, oops, I forgot the 7. Silly me. 8 times 7 times 6, and I'll stop at 5 factorial because I saw on the bottom 5 factorial. So I end up with 8 times 7 times 6, which is 336, just like we got up here. So again, this will get any problem correct. I like this because it kind of visualizes what's happening a little more. Alright, I'm not sure how much time I've used. I have one more topic. I think maybe I have one more topic. I think I'll stop there. You had a big test today, so I'll just put this little bit of information on permutations. So we're going to expand that next time to include distinguishable permutations and combinations. So that's what's next on the horizon. All right, class, carry on.